We will see the problem number 2.13. C. They give one statement that for given bias current, the minimum allowable drain source voltage for operation in saturation can be reduced only by increasing the width and hence capacitance of the circuit of the transistor. We will discuss that later here, but let us first see the FT. We have to prove that FT is this with the square law characteristics of the MOSFET. Okay, so we know the equation of FT. We know the equation of GM, and this important relation has to be remembered, that is CGS plus CGD is almost equal to COX W into L. If you will club those together, mu n COX W by L, VGS minus VTH, that is GM over 2 pi COX W into L. W will cancel out, COX will be cancelled out, L will be come down at the denominator, come to square term, turn into square term. So FT will be mu n VGS minus VTH in bracket upon 2 pi into L square. Alright, now let us discuss that thing. Let me keep the book here. Okay, so this is what I am trying to explain you. So if I bias current is constant, you know the current equation, that is I mu n COX W by L VGS minus VTH square. This is constant. You have 3 degree of freedom, that is WL and VGS. If you want VGS less, why? Because VDS should be greater than VGS minus VTH, okay, to maintain the saturation condition. But if VGS minus VTH itself is low, that is VGS is low, then what we need to do, we need to higher the W. So what that means is, if you want lower bias voltage here, don't confuse between bias current and bias voltage. I'm talking about the DC gate voltage. If you want to bias it with lower gate voltage and you want exactly same current as before, what you can do, you can increase the width of it, or else you can decrease the length of it, but we are not discussing length because length can be limited by foundry. So this is what it is telling. So what it will do, W, if we will going to increase, we will going to increase C also, CGS CGD, what I'm writing, CGS and CGD. So this is actually a practical situation at where you need to consider this. Okay, this is NMOS and this is PMOS. Let's say you have the bias PMOS and input input NMOS. What I meant, the amplification device will be NMOS here. If you want same I, your power budget is limited and you want higher headroom here, higher headroom. So ultimately what I'm trying to tell, the overdrive voltage, minimum requirement of overdrive voltage will be less. That is minimum. If you want, what you can do, VGS you can go lower, simultaneously you should make W high. Ultimately you will end up with higher CGG. GG means the gate capacitance, total gate capacitance. Okay, that has to be in your mind. Sometime you will not get the your operation of frequency by this CGG. Let's say you are tuning your LNA. This is your gate inductance, source inductance. Ultimately, if you will see, LS 1 over CS, GS obviously CGS, and this is L source, this is L gate, sorry. Okay, so if you will find the total impedance, if C is higher, you will find some lower impedance there. So if you want to match with 50 ohm, you will not able to get perfect match here. It may be possible there. This is just an example. The other thing what they are telling from this equation, that how the speed is limited as device is designed to operate with lower supply voltage. If you want this NMOS to be operated at lower supply voltage, that means you want minimum overdrive voltage. That means VGS minus VTH is lower, so FT will go lower. Ultimately, your frequency of operation will be limited. Okay, because see, you can't reduce your L after one limit. Let's say I'm using 22 nanometer PDK. After 22, what I will do? There is no option to go below that, right? So the only option is here to make it I mean, see, the FT can't go above some limitation with respect to VGS minus VTH, and this parameter we are trying to decrease. Okay, so this is how our speed will be limited if we want lower supply operation. You should be always take care with your RF circuit as such, as especially RF, because RF will be operated as a higher in the higher frequency operation. So your NFET will not able to give more gain at your interstate frequency, let's say 2.4 gigahertz for Bluetooth. Okay, so for that you have to increase your power supply. Of course your power dissipation will be higher, but your VDD should be larger. Your overdrive voltage should be somewhat larger, such that your FT can go up to your limit. Your limit, what I meant, whatever your interstate frequency is, your FT should be at least 6 to 10 times more than that. So to get that FT, you need to increase your VGS minus VTH. Okay, so this is how we are looking into design with respect to this basic concept. So this exercise is not just for just sake of doing. You need to understand why this FT is important, why this term VGS minus VTH in this equation is important, in this one why capacitance are important, GM and all. All right, thanks.